Hello. Okay, Elijah. Thank you for joining us since you just joined. So I'm going to be starting now.
Recording in progress.
Okay, so I'm just going to be starting now. Okay? So good morning, everyone. Today we're going to be talking about survival analysis in R, modeling time to event data. So I'm just going to be explaining some of the theory before we go dive into the practicals. So it's all going to be theoretical from the beginning, but not much, just to understand the concept, which might be actually new to some of you. Then we now show you how you can actually do this in R practically. So first of all, we need to understand what the concept of survival analysis means. So what does survival analysis means? So survival analysis is a collection of statistical methods for analyzing time to event data. So we have some kind of data which actually contains time.
Hello.
Yeah. Okay. Excuse me. I'm there. Hello. Did you want to say something? Okay, let me check. I'm coming. Okay. I think I know what the problem is. Hello. I'm speaking. Am I still being? Can you guys hear me? Can you still hear me? Can anyone hear me? What's happening? My audio is on. What is?
Hello, Ridwan.
Yes. Can't you hear me?
Hello. Hello, Ridwan.
I'm hearing you guys. I can hear you
Hello.
guys. Oh,
It seems we can't hear you.
I'm coming.
Hello. Hello.
I'm trying to see what the issue is.
We can look into. Now, coming. I can't hear. Okay.
Can you hear me now?
So can everybody confirm that they can hear him? Maybe I have a fault on mine.
Can you hear me now?
Hello?
Can you guys hear me? Hello? What's going on now?
So Ridwan, I don't know if you can check your end there.
It's showing that.
Let's pause the recording now.
Okay,
Recording
can you guys hear
stopped.
me? Can you hear me now?
Okay, yes, we can hear you now.
The
I think we
Zoom
have
was
to
using a different
restart it.
mic. Sorry about that. I just found out now.
Okay, maybe let's start again then. Thank you so much.
Okay. So I hope I'm being heard now, right?
Yes.
Okay. And everyone can see my screen.
Now. Don't worry.
Okay.
I think so. Yes. So we'll start the recording back.
Okay.
Yes, everybody.
Okay. Good morning, everyone. Sorry about that, please.
Recording in progress.
Sorry about that. So today we're going to be talking about survival analysis in R, modeling time to event data. So it's split into two sessions, a little bit theoretical, but it's not that deep, just for you to understand the concept, which can be new to some of us here. Then we now go into R to see how you can actually conduct this in R. I'll also be explaining the applications of this in various scenarios in healthcare, which is mostly used and also in other aspects of life where survival analysis is used. So first of all, we need to understand what the concept of survival analysis is. So what do we mean by survival analysis? So survival analysis is just a collection of methods which you can use to analyze time to event data. There are two key things when we talk about survival analysis: time and event. If the data doesn't have time, then you have no business running a survival analysis on it. So your data has to have time, and this time is not just any time. It is should be the time to an event occurring, because some data have time, but is it time before an event occurs? Because we have other data that are time series data, but they are not actually time to event data. So this is the key things that requires your data, that requires you to for you to be able to conduct a survival analysis on your data. So you need time to event, the duration until a specific event occurs. A patient is on a medication. We're expecting recovery or death because he's not feeling fine, which is why we give this particular patient medication. So we're expecting at the outcome of some days after taking the medication, it's either that medication is successful or the medication fails. So the event we're expecting now is death. So we're expecting the patients to recover or die within that particular period. So that is a time to event. We are now recording the time. Is it 2 days? Did they take the patient 3 days or 1 month or 2 months? So this is the time to event. So usually developed for studying death survival, but it's already been used in various places of life. For example, now even manufacturing companies, they usually use they call it failure, time to failure. So of an equipment failure, maybe they're testing new equipment. Which time does the equipment? How long? Okay, let me give this example now. Battery. A company produce a new battery. So time to that particular battery is going to die completely, or whereby the cells in the battery are no longer useful. So you can use survival analysis. Even in customer churn or employee churning, you can use survival analysis, whereby your event is now employee leaving the company or the organization, or your customers stop buying from you. So it's not just in health, but most of the time survival analysis is known to be used majority in health, but these are other areas whereby you can use survival analysis. So someone might ask, why is it that we are not using standard methods? Then the problem of using standard method is that we have what we call censoring. So censoring is a situation whereby you are conducting an analysis on someone within a period. Don't forget we said survival analysis is time to event. But after that particular time you have already put, or your study time, then the event did not occur. The patient did not die. Now, after that, you don't know what happened to that particular patient. He might died the next hour after your study, or the next day after your study. So the patient has still later died, but this is not something you know about. So this is what we refer to as censoring, incomplete observations. Observations that nothing has happened to them throughout the period of the study, or we did not know how they end up throughout the period of that particular study. Also, survival data tends to be usually non-normal distribution. So this is why we usually consider survival analysis. More times the data might not be normally distributed, which means that when you try to plot the distribution on a graph, you are going to find the distribution is not having a bell-shaped curve. So in such situations, you are going to use a survival analysis. And also time-dependent covariates. So covariates are more or less like the variables that are dependent on the variables that actually the outcome is dependent on. So most of these particular variables depend on time, because that time is a major factor. You are trying to see how a patient will survive before a particular time. You have to record the patient age, the kind of drug you take. Maybe you have 3 drugs, you gave it to various patients, the patient's race. So these are things that is going to affect that particular patient surviving to that event. So you can see that most of these variables are dependent on time. And also we have the interest in hazard rate. What is the hazard of this particular patient experiencing this outcome compared to another patient? So because of this kind of things that we're interested in, we consider to use survival analysis instead of other standard methods. A typical example: a patient enters a study on day 0 and is followed for 2 years. If they are still alive at the end, we know they survived at least 2 years, but we don't know their actual survival time. After 2 years, the patient might die. or the patient might still be alive. So our belief is just that they survived for 2 years throughout the period of the study. But after the study, we don't know what happened to those particular patients. So key concepts. The key concept of survival analysis is censoring. It's very important. So censoring occurs when we have incomplete of information about survival time, which I just explained recently. We have 3 types of censoring. The first is the right censoring, and is the most common type of censoring you occur anytime you have a survival data. First of all, the event has not occurred by the end of the study. That particular patient that you are tracking or you are monitoring, that particular patient has not died before the end of that particular study. The patient might have died after the study has ended. That is still a right censoring. Or the patient was lost to follow up. Lost to follow up in the sense that this particular patient you are monitoring just stopped coming to the clinic, stop participating or stop answering your calls. That patient, you can't monitor that patient again because you have no way of contacting that patient. So that is another example of right censoring, and we can say that individual has been lost to follow up. Next is patient withdraws. So patient withdraws means that the patient left the study. Instead of just disappearing, the patient told, I don't participate in this study again. Take me out of this study. You might not take the patient out of the study, even though the patient say you might stop monitoring the patient, but that doesn't mean you remove the patient from your data because you already have information on that patient already. So this is another scenario of censoring. Then the next is left censoring, which is very rare. Left censoring occurs whereby the event occurred before the observation began. Before you started your study, the patients have already died or the patients have already left the hospital, things like that. So you have not even started your study already and something happened to the patient. So these are an example of left censoring. Then the next is interval censoring. This situation whereby events occurred between 2 observation times. So maybe the patient left and came back again. So you can see it has been censored within a particular time interval which you have no information on that particular patient. So this is a visual example of censoring. If you look at this now, you can see we have patient 1, we have patient 2, 3, 4, and 5. So at 8 months, you can see patient 1. So this dark dot means censoring event has already occurred. That means the patient died or the patient survived the study. While this white dot means that the patient is actually censored. So if you look at this patient 1 event at 8 months, maybe the patient died. Patient 2 also died at 15 months, or maybe 15 months the study ended, the patient actually survived that particular 15 months. Then if you look at this one, is white, which means it was censored at 20 months. The study has already ended. So this particular patient now, he survived the study. So meaning that we don't know what happened to him at the end of this particular study. Then patient 4 also censored at 10 months. The patient was lost to follow up. Then we have patient 5 where an event happened at 5 months. So this is just a typical example of censoring. Most of the times you are going to be coming across right censoring. You are going to be coming across right censoring instead of left censoring or interval censoring. So we have what we call the survival function, which is just the probability of surviving beyond time t. I have 20 patients. What's the probability that this patient survive beyond a certain time? The period of my research is for 2 years. What's the probability that what is the probability of surviving up to 2 years? Some can survive for 1 year, some 1.5 years, some 8 months. So the probability of surviving beyond a particular time t is what we call the survival function. So the properties are what of the survival function. At the first time of the study or at the beginning of the study, the probability is usually 1 because everyone is alive. And at the end, everyone's already experienced the event. At the end, you have probability of what? 0. And the probability survival function is a non-increasing monotone decreasing, which means that what? Because probability of surviving starting from 1 is going to be falling down the graph. It's going to be falling down up to 0. You can't have a survival function that is going up because we expect people to be experiencing events till the end of the study. So we also have what we call the hazard function. I'm just putting the mathematical equations there, but what is most important is just to understand the concept. So the hazard function is more or less the risk of events at time t among those who have not experienced it yet. You are conducting a study and people have already died, or patients have already died inside that particular study. So what is the risk of this particular event happening at that particular time among those who have not experienced it yet? So this is different from the survival function, which is probability of surviving at a time t, but this one is the hazard or the risk of having an event at time t. So risks can increase or decrease, or it can stay constant over time. Another thing is that unlike that other one I just mentioned, which is probability, and we know probability between 0 and 1, the hazard function can exceed 1. So because we are trying to find out the risks of an event happening at time t. So what is the data structure of a survival data? For you to conduct a survival analysis on your data, you have to have these three things, or your data have to meet these three conditions. First of all, you have to have time, and not just any time. This time should be the duration from start to event or censoring. For example, I'm conducting a cancer study on a particular medication, and I'm trying to see what is the effect on those that have cancer. The study is for 2 years, and I already have 100 patients in this particular study. So what I'm going to do is that in my data, I have to have the time, because out of this study, there will be individuals that might die from the study. So I have to have the time from the beginning of the study to when that particular individual die. That is the time to the event. I also have to have the time to when an individual will leave the study or withdraw from the study. That is the time to censoring. So that is that particular first factor. The second category is the status. Did the patient die? 1, that is the event has occurred, or the patient was lost to follow-up, or the patient did not die before the study ended. Because if a patient did not die before the study ended, it's still censoring, because we don't know what happened to the patient after the study ended. So we are still going to record it as 0. Then the third factor is covariates. These are usually variables that might affect survival. Patients might survive based on various factors. We have age, we have treatment, we have race, we have other factors that can be used in your data. So these are usually referred to as covariates, and they are variables that might affect survival. So these are the 3 factors that you need for you to conduct your survival analysis on a data, or the conditions that your data need to meet for you to consider using survival analysis. This is an example of a data. You can see we just have 3 patients here, patients 1, 2, and 3. And first of all, start with patient 1. Patient 1, this is the status of patient 1. Patient 1 died, 1. And it took patient 1 15 days. Let's take this as days. It took patient 1 15 days before dying. And patient 1 received treatment A, and also the age of patient 1 is 45. You can see we have 2 variables. The second is time. The second one is the second one was censored. So either this particular patient left before the study ended, or the patient actually survived the study, which also means we are censoring that particular patient. So this patient's time was 20. So this 20 might be the time the patient reached before the study ended, and this was the treatment the patient received, and the age of the patient was 52. Likewise, if you look at this also, the time was 8 days before the patient died. The patient received treatment A, and the age of the patient is 38. So this is just an example of how survival data looks like. So what are the common applications in biostatistics of the common applications of survival analysis in biostatistics? Because that is mostly where it's usually used. First of all, in clinical trials, most pharmaceutical companies use survival analysis a lot. In fact, it's one of the most popular statistical analysis that pharmaceutical companies usually use to conduct clinical trials, because they need to see the effect of that particular drug, and they will treat that different drugs they have as covariates when trying to check the time to event of various patients. We also have epidemiology. In epidemiology, they are interested in time to disease onset. Then we have cancer research, where we're also trying to look at overall survival or progression-free survival. We have infectious disease, time to infection or recovery. If you look at all of them, there is time to something. So the key thing here is time to events that you're interested in. We have cardiology, time to heart attack or stroke. We have health economics, time to hospital readmission. A patient has been discharged already. When is this patient coming back to the hospital again? You can use survival analysis to also for that. We have various types of survival analysis method. We are going to be treating only two. So the third is more or less an advanced method of survival analysis. The most common is usually the non-parametric method, and we have the Kaplan-Meier estimator and the log rank test. While the second is semi-parametric, which is also known as the Cox proportional hazard model. The others are parametric methods, exponential, Weibull, and log normal models. So the reason why they are not common is because most of the times your survival data will hardly follow the assumptions of a parametric distribution. So that's why the non-parametric method and the semi-parametric methods are usually popular. The Kaplan-Meier curves. So the Kaplan-Meier curve is a curve that, the Kaplan-Meier estimator is a parametric method that allows you to estimate the survival function of survival times. So it has various names as product limit estimator, KM curve, or survival curve, and it handles sensor data naturally. So this is just the formula for calculating it. We have 1 minus di over ni. So this is product. This particular sign is a product. Just look at this. The next table I'm going to be going to, you're going to understand what this particular formula is going to, how you can use this particular formula, because this is what R we use to plot the graph, your survival curve that you have. We'll just have three important parameters here. The number one is the distinct event times. Then the next is number of events at time t, and the next is number of risks before ti. So this is a simple example demonstrating the Kaplan-Meier estimator. If you look at this now, we have the time. You can see we have the at risk. At risk is the number of inpatients at that particular time. Why the event is the number of people that experience events at that particular time. Then the censored is whether the event happened or the individual was censored. Then we have survival probability. Now, if you look at this at time 0, which is the beginning of the study, we had 10 patients. Then these 10 patients, nothing happened to any of them. None of them died, and none of them were censored. So we are now going to, based on this particular formula, we are going to take the number of events at time t, which is at time 0, divided by the number at risk before that particular time. So you can see the number of events at time 0 is 0, divided by the number of at risk, which is 10. 0 divided by 10, we have 0. Then we now say 1 minus 0, which is going to give us 1. Then at time 3, we have 10 at risk. 10 of them at risk at time 3, but one of them died at that time 3, which can be after 3 days. But none of them were censored after this particular time. So we're still going to say 1 divided by 10, which is going to give us 0.1. Then 1 minus 0.1 will give us what? 0.9, based on that Kaplan-Meier estimator formula. So 0.9, we will now multiply it with 1, because this formula has a product sign here. So it's more or less like a cumulative probability that we're getting. So we're going to multiply 0.9 with this one. Then we get the survival probability for those under time 3. When you go to time 5 too also, the number at risk is 9, because 1 has already died here. So 10 minus 1 here will give us 9. So the number of risks here is going to be 9. But none of them died at this particular time, and only one of them was censored. The Kaplan-Meier estimator will don't take into account the censoring. So I'm just going to say 0 divided by 9, based on the Kaplan-Meier estimator formula. And we are going to now subtract 0 from 1, still based on the formula. Then anything we get, 1 minus 0 is going to give us 1. So that is where we get this 1. We now multiply it with the previous value we had here, 0.9, and you get 0.9. Same thing to also at time 7. The number of risks is 8, because don't forget that 1 is already censored. Maybe it's lost to follow up. So the number of risks has reduced to what? It has now reduced to 8. But 2 people died at this time, and nobody was censored. So we divide 2 by 8, and anything we have, we subtract it from 1. Then we now multiply it with the previous survival probability. So that is where we have 0.75 times 0.9. Then we have 0.675. Then at time 10, the number at risk is 6 because 2 have died already. So you can see we have 6. Then the number of people that died is 1. Then we divide 1 by 6. We subtract it from 1. And anything we have, we multiply by the previous. So assuming this was the final time of our study, this is now going to be your survival probability for this particular study, 0.562. So the probability of surviving at each of this time is now your survival probability. So probability of surviving at time 0 is 1 because nobody died. Probability of surviving at time 3 is 0.9. Probability of surviving at time 5 is 0.9. Probability of surviving at time 7 is 0.675. Probability of survival at times 10 is 0.562. So this is how the Kaplan-Meier estimator works. It's very important because this is what you use in getting this particular graph, which I'm going to be coming up next. So how do you interpret your KM curve? So we have what we call KM curve. Before I proceed, does anybody need any clarification before continuing? Hello? Okay. Okay. Did I went out of the Zoom meeting? Am I still there?
Yes.
Okay. Because I thought that I'm out of the meeting. That was why I was trying to confirm. Okay. So interpreting the KM curves. The KM curve is a graphical way of understanding the survival of patients in your study. So we usually have what they call the y-axis, which is the survival probability, and survival probability is usually 0 to 1. Then we have the x-axis, which is the time. Then we have step functions. So it's just that a way of saying the curve actually drops. Then we have vertical tick marks, which you will see later on now in the graph, which is the censoring, and we have confidence bands that shows uncertainty. So these are the things you are interested in when you are trying to interpret your KM curve. First of all is the median survival time, then the survival at specific time points. Your shape of the curve, it should be steep and gradually decline, because I told you that the survival curve should be something that is going down, since the probability of surviving is going to be reducing as time goes on, and also comparison between groups. So what is our median survival time? The median survival time is usually a time at which 50% of the subjects have experienced an event. So for you to have a median survival time, 50% of subjects should have already experienced that event, maybe die or maybe have a disease. Any event you are trying to measure, 50% of the individuals in that particular study should have already experienced that particular event. So the survival probability at the median survival time is usually 0.5, and usually more robust than the mean survival. So instead of using the mean survival, we just use the median survival time. And it may be undefined. I already told you, you have to have 50% of subjects for you to have a survival time, or more than 50. So if you have less than 50 experiencing an event, then your median survival time might be undefined. So if the curve never drops below 0.5, then we surely say the median survival time is not reached. This is the example of a Kaplan-Meier curve, and this is for lung cancer patients. You can see in this we have two parts. The first is our graph, then the next is a particular table here. So let's focus on the graph first. You can see our x-axis, which is the time, and you can see our survival probability in the y-axis. You can see from 0 to 1. I told us the range of the survival probability. At the beginning it is 1. You can see it drops to around 0.1 something at the end. You can see it. Now, what is our median survival time? Our median survival time has to be the place where survival probability is 0. So you need to trace this particular, if you look at my cursor, this particular line where the survival probability is 0.5, you need to trace it to the line, and anywhere it meets, you come down. This is your median. This is your median survival time, which is 300. So after 300 days, you have reached the median survival time. So the median survival time of individuals in your study is 300 days. Now, this table shows you the number at risk. At time 0, 228 individuals are at risk of dying because you are just starting the study. At time 100 days, 196, because a few of them have already experienced their events, or maybe they have been censored. If you check the now last time, only 2 individuals survived at time 1000. So this is the number of individuals that remain in this particular study. Now you can see some marks in this particular graph. If you look at it very well, you can see some ticks. These ticks indicate censoring. So it means either the individual, most of the time, say, when you see these marks here before the end of the study, it's either that particular individual was lost to follow up, or the individual did not experience the events up to when the study ended. So this is the meaning of this particular mark that you are seeing here. So we can also compare survival curves. I just showed you a single survival curve now without any covariate. But what if you have covariate? What do you do? So this is where you have this kind of curve. Now, I'm comparing the survival now by age group. I've broken the patients in that particular data now into various groups. We have 3 age groups now. We have less than or equals to 60 years. We have 61 to 70 years, and we have greater than or equals to 70 years. If you look at this particular curves now, you can see some of them have higher survival probability compared to the others. For now, if you look at the survival now of those that are less than or equals to 60 years, it is higher compared to those between 61 to 70 years, and also higher compared to those that are greater than or equals to 70 years. Just like the other table I mentioned now, we have the number at risk and also the age group. Now, there are some key things you should know. That when anytime you see a curve cross when you're comparing survival, then it means non-proportional hazard. And also, if you see a curve non-overlapping, it suggests difference. Let's say, for example, now, if you see a particular curve, like this curve, this red one only touched the blue one at this point. So you can see there's a little bit difference between it. But if you look at the p-value safe, I'm going to be talking about the log rank tests any moment. You can see that it's showing that there is no statistical significant difference, because the p-value has to be less than 0.05 for it to show a statistical significant difference. Though it is still a little bit low, but not low for us to show statistical significance, because this line here just touched it in this particular place. So the Kaplan-Meier curve is more or less descriptive, and we will talk about the limitations, why you should also consider the Cox regression. First of all, there is no covariate adjustment. It cannot control for confounders. So confounders are usually variables that affect your outcome, whereby if you have that particular variable, you notice that your outcome is changing between members of those of various groups under that particular variable, and it is only descriptive. So the Kaplan-Meier curve doesn't quantify effect. It just shows, you can see it's just showing us the survival. It doesn't show us which particular group has more hazard. It's just something descriptive. So it doesn't show anything deep that can actually be useful for us. The third one, it is limited to categorical comparison. So you cannot use continuous variables, because if you have continuous variable like age, how can you use it? So for you to be able to use the Kaplan-Meier curve, you need to just break down age into categorical. If you have something like BMI, you need to break BMI into categories. If you have something like weight, you need to break it into categories. So that is also one of the limitations. Then it assumes independence. So issues with competing risks and also small sample problems. It's usually unstable at the tail of the distribution. So these are some of the limitations of the Kaplan-Meier method. Then, but it's usually ideal when you're trying to describe survival experience or you are trying to conduct initial exploratory analysis, and we are also comparing 2 or 3 groups visually. So if you have like a factor or a variable with 7 groups, it's going to be very difficult for you to use the Kaplan-Meier curve to understand what is happening between members of that particular group. And also easy to communicate with non-statisticians because they can see the graph. Okay, from the graph they can know that okay, this particular group have higher survival probability compared to these groups. So you should use it with caution when you have many covariates or when you have small sample size or your data is heavily censored. When your data is heavily censored, it means that less than 50% of the individuals in your data have experienced the event. So let's say out of 100 patients that you are studying, only 20 of them experience the events. The Kaplan-Meier curve is not actually the good option that you should use. So we have what we call the log rank test. So the log rank test is usually used to find out the significant difference between 2 groups. In the log rank test, we have 2 hypotheses. First of all is that the survival distribution are the same across groups. Let's take, for example, now gender. The male and the female have the same survival distribution. That means none of them actually, the survival of none of them is higher than the other. So they both have equal survival. Why the alternative hypothesis is that one of them differs. Maybe the male survive more compared to the female, or the female survive more compared to the male. So this is the purpose of the log rank test. So for you to interpret the log rank test is using the p-value. If your p-value is less than 0.05, then it means you reject the null hypothesis, indicating there is a significant difference between the survival in both groups. Why if it is the other case, if it is greater than or equal to 0.5, then there is no difference between those particular 2 groups. So, but there are some important notes. First of all, it's a test for the equality of entire survival distributions, and also it does not specify which group is better. If you use the log rank test now, if you have 3 groups, like the age we did earlier on now, it can only tell you that, okay, there's a significant difference between 3 of them. But it's possible that out of those 3 age, 2 of them are not significantly different, but one of them was different. So the log rank test will not actually tell us which of them is it. So it doesn't quantify magnitude of difference only. We only know that there is a significant difference between 2 groups, male and female, or between 3 age group, or between 5 race. But what is the magnitude of that difference? It doesn't tell us that. And also, you have to look at your KM curve for the direction and also the clinical significance. So when you try to report your log rank tests, you are going to be having some of these particular informations that you have, the test statistics and the degree of freedom. You are going to get your p-value, also your sample size, and the event numbers per group. If you have 2 groups, male and female, what is the event? How many of them experience the event in each of that particular group? You also have the median survival times with CIs, your KM curve figure, and also clear statements of findings. So example now, the log rank test showed significantly better survival in the treatment group. So this is the treatment group. Chi-square is equal to 8.42. And you have the degree of freedom of 1 at 0.04. So you can see our p-value is less than 0.05, which means there is a significant difference between the survival treatment between survival in the 2 treatment group. Let's say one was giving treatment A, and the other group was giving treatment B. The next is the cost proportional hazard model, and this actually solves all the limitations of the previous techniques I've already explained. So the cost proportional hazard model is a semi-parametric regression method for survival data. So why it's mostly is because it's multivariable. You can add a lot of covariates to it. Like now, if you look at the Kaplan-Meier curve we did earlier on, we only took age. But what if you want to check age and gender, or age, gender, and treatment, or age, gender, treatment, and race? It's going to be very difficult. So this is one of the challenges that the cost regression is trying to solve. So it estimates effects of covariates on hazard, and also there's no assumption about the baseline hazard shape, and you can even include multiple predictors, which I already explained, and it also handles both continuous and categorical variables. So just like your regression equation, if you are familiar with it, the Cox model just look like this. The only difference is that you have what you call the baseline hazard here. What is the hazard if every other variables were kept constant, and you take the exponential of all of this? So this is just the mathematical representation of the model. So how do you interpret your Cox coefficient? So if you are familiar with interpreting regression coefficients, so this is actually a little bit different. So when you have a positive beta, it means that what you are likely to have an increased hazard, which means worse survival. If you have a negative beta, it means decreased hazard. If you have beta to be 0, it means no effect. But we don't usually use this coefficient when trying to interpret hazard of individuals in a survival analysis. We use what we call the hazard ratio, and the hazard ratio is usually the exponential of this coefficient. So this is one of the this is a kind of plot you can get when you conduct a Cox proportional model. When you build a Cox proportional model in R. So this is what we call a forest plot. Is this simple example now? We have 3 variables. We have age, we have sex, we have pH.ecog. So this is more or less like a clinical status. We have also pH.canu. These are 4 variables here. This first one that you are looking at is age. Is actually continuous. So we use the continuous version of the age in this example. And by this right hand side is what is our p-value. So you can see asterisks on some of this p-value, which indicates statistical significance. Now, anytime you exponentiate your coefficients to get your hazard ratio, if your coefficient is 0, which means no effect, you get 1. If you get an hazard ratio that is 1, it means there is no effect. So that means you are not going to be, it doesn't have any effects on the hazard of that, that particular variable has no effect or no contribution on a patient surviving. But if you have hazard ratios that are far on both sides, either on the right or on the left, both have their respective meaning. Consider that of the sex that you're looking at now. Our sex is into 2 levels, male and female. We have 136 male, we have 90 females. The male is usually the male is the reference value in this scenario, because this is the reference we are comparing to the male now. So that's what reference category means. We compare to the male. Now look at the female. The hazard ratio is 0.56. So what does 0.56 means? It means that females have a lower hazard. The hazard of them dying is 0.56 compared to male. That is what it means. So the hazard of females dying compared to the male is 0.56. Assuming it was not 0.56 now and we have something like 1.69, it means that the hazard of females dying is 1.69 more than that of the male. So if it was on the left hand side, that is before 1, then we said what is a low hazard. That particular group have a lower hazard of experiencing that event or outcome compared to the other group. But if it's on the right hand side, we say that particular group have a higher hazard of experiencing that event compared to the reference category. So even if it was 3, that's how you do it. Let's say, for example, now we have let's say treatment A, treatment B, treatment C. Treatment A is now going to be your reference category, and you still interpret it based on the way I just did for that of male and female. So treatment B, you look at what the hazard ratio is, you compare to the male. Treatment C, you look at what the hazard ratio is, you compare to the male. So for pH.ecog and pH.canu, these are both continuous variables. So that is why you can see we have no categories here. So how you explain or how you interpret continuous variable is that when you see the hazard ratio now, you can see for pH.ecog is 1.88. So which means what? The higher your pH.ecog value, then the higher your hazard of experiencing that particular event. For this one, we cannot interpret this because it's not actually statistical significance. So this is how you can interpret your Cox coefficients when you are trying to conduct your Cox proportional model. So for categorical predictors, one category is usually the reference, and the coefficients represents the log hazard ratios versus the reference. And you can also have multiple categories. So this is what I just explained now. You have treatment A and treatment B. Treatment A will not be your reference when you are now interpreting treatment B. So by interpreting treatment B, you're already knowing what can also happen to treatment A. So what is treatment B hazard compared to A? Is it higher or it is what? It is lower. So that is how you interpret categorical predictors. Why for continuous predictors, you are going to be, it's just based on the value. If it is age, then you can, if the age is having a higher hazard ratio as it increases, or is it as the age increases, the hazard ratio is actually what? Decreasing. So the coefficient is per 1 unit increase, and you assume a linear relationship with the log hazard, and you can transform the age if needed, maybe using log or polynomial transformation. And you can also categorize it. You can categorize your age if you prefer to see how various groups of the age are being affected. So for multiple predictors, Cox models can include many predictors simultaneously, because by the time you add multiple predictors, you control for confounding. It's possible a particular value or a particular variable is affecting the survival of patients. But when you now conducted your Cox model, you now found out that that particular variable is not affecting the survival of patients. But when you now included another variable, you now find out that variable that you included is already making that other variable affect the survival of patients. So that other variable included in the model is called a confounder. Typical example now, by adding age, you found out that age was not affecting the survival of patients. But when you now added their gender, you now find out that those that are even male have already affected that particular age, because you find out that those that are male, the age factor is affecting them, and those that are also female is also what's affecting them. So for you to conduct a multiple predictor, you need adequate sample size, and we are talking of events. So you have to have a high number of events, not just subjects. And the rule of thumb is that you should have greater than or equals to 10 events per predictor variable. So what are the advantages of Cox model? First of all, it is semi-parametric, which makes it flexible, and it's also robust. It can handle various distributions, and it is multivariable. It controls for confounding, and it's also efficient. It uses all available data, and also it is interpretable because of the hazard ratios, and is widely accepted in medical research. So the limitation of the Cox model is the proportional hazard. It may not always hold, and we have complexity. So it has a lot of assumptions compared to the Kaplan-Meier. You know, the Kaplan-Meier is just descriptive and it is purely non-parametric, but the Cox model is semi-parametric. And also you need to have a lot of events. When we talk about events, is those that maybe have died in your study, or maybe those that are trying to experience, that might have experienced something or an event you are trying to study. Non-linearity is also another limitations. You have to actually transform. For example, your age. If you find out that there is no linear relationship between maybe your age and the outcome, the log of your outcome, then you need to transform that particular age value. And also no absolute risks. You only have relative comparisons. And also in terms of competing risks, you need special handling. So I think I've already explained most of this particular hazard ratio. So these are various information I've already explained earlier on. So you can see hazard ratio of 2, twice the hazard. 0.5 means half the hazard compared to the other reference category. And this is how you can transform the hazard ratio to coefficient to hazard ratio. You take the exponential of your coefficient to get hazard ratio. Why hazard ratio to coefficient? You take the natural log of your hazard ratio to get the coefficient. And percentage change is usually your hazard ratio minus 1. If your hazard ratio is less than 1, you say 1 minus your hazard ratio. But if your hazard ratio is more than 1, you say hazard ratio minus 1, you get the percentage change. So this is just a simple example showing the conversion between coefficients and hazard ratio. And you can see here hazard ratio is 0.625. So 1 minus 0.625, we get that is 0.375. And 0.375 means that what? The hazard of death from the new treatment is 37.5% lower compared to the standard care. So this is an explanation of how you can also interpret the hazard ratio in terms of percentage. So for continuous predictor, you can see our hazard ratio here is 1.03. So for each additional increase in age, the hazard of experiencing that particular outcome, which is death, increases by what? It increases by 3%. I told you it's going to be 1.03 minus 1. So which we get 0.03. So 0.03 is 3% increase in the hazard for every year increase in age. So we have the confidence interval of your hazard ratio. So what your confidence interval is the range of your hazard ratio, because that hazard ratio is an estimate, but the confidence interval gives you a range that, okay, even if it is not that value, your hazard ratio is not going to exceed this range. For example, 0.47 to 0.84. So this is the hazard ratio 0.62. So what this is trying to tell us that even if the hazard ratio is not 0.62, it cannot exceed these two values. So the hazard ratio cannot be less than 0.47 and it cannot be more than 0.84. Where your hazard ratio is not statistically significant is if it contains 1. A typical example is 0.5 to 1.7. You can see that inside this particular confidence interval, you have 1 inside. So if your confidence interval have 1, it means it is not statistically significant. But if there is no 1, either 0.47 to 0.84 or 1.07 to 2.79, you can see that there is no 1 included in your confidence interval. You can now decide that your hazard ratio is statistically significant and proceed to interpret it. So the p-value is what usually lets you know if your hazard ratio is statistically significant. So if it's less than 0.05, we can see statistically significant. If it's not less than 0.05, then we can see it's not what statistically significant. While the confidence interval actually shows the range of plausible values that your hazard ratio can fall in. So we also have what we call effect modification, whereby you try to see interaction, which I already explained earlier on. So let's say, for example, now you are considering treatments. You now added gender as another variable. So it's possible that what the gender variable you added can affect that particular treatment variable, such that the hazard ratio for treatment in men is going to be lower compared to the hazard ratio for treatment in women due to that particular gender you have added. So it's possible that without that gender variable, you might find out that maybe the treatment might not even be statistically significant. But by checking for the interaction, when you are trying to, okay, let me put it in this case. In your study you are conducting, you have 2 treatments, A and B. So you now found out that the hazard ratio of those under this particular treatment is higher compared to those under this treatment. Then you now try to see how does gender now affect this treatment. Then gender will now let you know that, okay, even though the hazard ratio is higher compared to those on this, the hazard ratio of this treatment is higher, you now find out that the hazard ratio for each this treatment with the particular gender is higher compared to that of that other gender. So for treatment in men, it can be lower compared to that of women. Whereby if you not consider interaction, you might not be able to see that particular effect modification. So this is more or less like subgrouping the patient inside the data that you are having. So when you're trying to report hazard ratio, your point estimate, also your confidence interval, your p-value, and also your reference category for categorical variables, as also adjustment variables if you are considering multiple variables. Then your sample size and also your number of events. Then your interpretation. So if you look at this now, effect of drug X on mortality in heart failure. So treatment with drug X was associated with reduced mortality compared to placebo, because if you look at the hazard ratio is 0.68. So the hazard of experiencing that particular event is 0.68 compared to those that receive the placebo, after adjusting for age, sex, and disease severity. And also among 500 patients, 250 per group 180 deaths occurred during a median follow-up of 36 months, so which represents a 32 reduction in the hazard of death. So this is just saying 1 minus 0.68, which is 32%. So I already explained this, which is our diagram in this particular place that you are seeing. So I'm just going to go into arrow now to show us how you can conduct all what I already had mentioned. So let me switch my screen. Okay, so I hope you are seeing my screen. Okay, so is everyone seeing my screen? Okay. So you need to install these particular packages if you want to conduct survival analysis. The first is the survival package, then the next is the SurvMiner. Then we have this dplyr for data manipulation. We have ggplot2 for graphical or data visualization. So if you don't have it, you just install it. So I'm just going to run this. So we're going to be using this lung cancer data. So this lung cancer data has these variables. First of all is institution. Okay, let me just view it. Head lung. So this is it. The first variable is institution code. The code of the institution. This is also another. This can serve as a covariate. Then the next is the time. Very important variable. The time to events, either time to censoring or time to the event occurring. Then the next is status. So the status is either dead or censored, whereby 2 means dead while 1 means censored. We're going to be changing this to 0 to 1 because the survival, I think it's the survival package needs your status to be in either 0 and 1. Then we have the age. This age, you have 2 ways to go about it. You can either categorize it or you can work with it like that. Then we have sex, male and female. 1 is male, 2 is female. We have ph.ecog, which is the ecog performance, ECOG performance. And we have ph.kano, this Kanofsky performance. Then we have also pat.kano, Kanofsky performance score rated by patients. We have meal.cal, which is the calories consumed at meals. We also have the weight loss in the last 6 months. So these are the variables that we have. I think if you get your hands on this data, I'm not going to be using all of it. You can also try your hands on other covariates and see how they affect the survival of patients or the event of dying in this particular data. So we're going to be checking for missing values. So you can see under institution, we have 1 missing value, 1, 3 here, we have 47 here, we have 14 here. So you can, they are not much compared to the total number of observations we have. I think total number of observations should be, I think, okay, N row is 228. So total number of observations is 228. So we are just going to do some data cleaning in this place. First of all, we are recoding. This is we are using the mutate function to create some new variables. We are going to recode death to 0 and 1. So whereby 1 means dead and 0 means censored. Because our survival package wants us to use 0 and 1, not 2 and 1 that was used in the data. We also want to recode the sex to male and female. We are making it a factor. It's currently in numeric. ph.ecog2 also are making it a factor. The age group, we are categorizing it into 3 groups: less than or equals to 60, 61 to 70, greater than 70. And we're also removing the missing variables. So we'll just run all of this now. And this is just a summary of our data. So this is the summary of our data now. We have removed the missing values. So you can just use this to have a glimpse of the data. You can see under age group we have 94 that are less than or equals to 60 years. 88 of them are between 61 to 70. While greater than 70 we have 46. You can also use that to observe other variables that you have in your data. And before you conduct your survival analysis, you need to create what you call a survival object. So survival object is what you are going to use to conduct survival analysis, and you can create that using the solve function. The for function takes 2 major arguments: the time and the event. These are the 2 important things in survival analysis. The time, which is we have already created a time. So we already have a time variable. If you check our data earlier on, we have a time variable already. This is it. And the event, which is that particular column we just created, date, whereby we recoded it, date to represent 1 and censored to represent 0, where censored can be either lost to follow up or survived beyond the study time. So we just create this now using the solve function. Then the next is to view the solve object. So this solve object now is the various times. Let me just run it complete so that you see it. Solve object. Look at this. If you look at it now, there are 222 observations here. Each is the timing of each particular observation. Any place you see plus, it means censored at that time. This particular individual in this observation was censored. Censored at this time, censored at this time, censored at this time. So these are censored observations anywhere you see plus. So these are the timing in all our observations that we have. So this was what was created in the solve object. Now, you can just have a summary of your solve object. You can see your minimum time is 5. This 5, I think the 5 was it in days, is in days. The 5 is in days. And the maximum time is 1022. So in days. So I think this should be more than 2 years or even 3 years. Then we want to create a survival curve now. If you want to plot your survival curve, you need your solve fit function. So this solve fit function is going to take your outcome and your predictors, or since we are using Kaplan-Meier, your outcome and your categories. If you are not putting any category, you just want to see the survival time of patients in your data, you put 1 here. So 1 means you are keeping all variables constant. You are not interested in seeing the survival probability of survival between various categories. And the next argument you are going to be providing is your long clean data, which is the data we just created earlier on, the cleaned one. So you just run this to get your KM fits value and you get the summary. So this is the summary here. So this is the number of individuals, which is 228, and the events is 165. 165 of them died. This is the median survival time. So the time at which 50% survival probability was reached is 310. And we have the lower confidence interval and the upper confidence interval of that particular median time. I thought that the Kaplan-Meier is descriptive, so the information we get is not much. You can check the detailed summary at different time points. So at different time points, which just specifies some time here in this particular summary function. So at each time, you can get the number at risks, the number of events. This table should look familiar to you if you are looking at it. It's that same table I used earlier on to explain how you can get the Kaplan-Meier estimate. You can see at various time, the number at risks, the number of events, the survival probability. You can see it's decreasing. In the beginning is 1, at the end we get 0.142. So you can actually change. I can add 800 here, 800, 900, 1000. Okay, so up to 1000. So you can see at 1000 number, this is the final survival probability. So it's decreasing. The survival probability is decreasing across time. So this is how you can view the survival probability of various of patients in a particular time. So we can plot our survival or our Kaplan-Meier curve. You can either use the basic plot function. This is the basic plot function in R, where you give your survival model. This is the model we got here. This model we got here, and you give your x-axis, the name of your x-axis, your y-axis, your title, and also do you want confidence interval to be displayed. So I'm just going to run this. So this is the curve here. So you can see it here. This is our survival Kaplan-Meier curve, survival probability. This dotted line, you can see two dotted line here. So these are the confidence interval, these two dotted line. While this dark one is the main or the estimates that we got from the Kaplan-Meier curve. Then we can use ggSolvePlot function. This is from the SolveMiner package. So this one gives us a much more colorful graph like the one you saw inside the presentation earlier on. So the arguments are just basic arguments, which first of all you give your model, then you give your clean long data set, your confidence interval is true. The risk table or that table you saw below the Kaplan-Meier curve I showed you earlier on, you give this as true. Also your risk table column, do you want it to be in straighter, GG team, your palette, then your title, XLab, YLab. So these are all basic arguments. The most important is just to give you this KMPUT and your data. So that's the most important information here. So just going to run this. Okay. I've expanded the curve. Are you seeing the expanded curve? Hello? Is anyone seeing the expanded curve here? I've expanded the curve. Can you see the bigger curve now? Is anyone there?
Yes.
Are you seeing the big curve? And the bigger, are you seeing it? I've expanded
Yes.
Okay.
Yes.
So this is the curve now. So I don't think this needs much explanation. I've already explained it. So this is our time. This is our risk table. So you can set risk from your argument. If you don't want it, you can remove it. This is your Kaplan-Meier curve. So you can see the probability is coming down. So at each time, you can see the survival probability. Okay, at time 400, the probability of people surviving in this study is 0.4 something. Or at this time, 0.3. So up to the end. So it answers a lot of questions. So this is just like a descriptive view of your data. If you need deeper questions, you need to go for the Cox model. So I want to stratify by sex now. So compared to the one we did earlier on, we see we put 1 in this place. But you want to stratify by sex, you just have to use your sex variable here instead of 1. You put it here, just like you do your normal regular regression using the regression LM function. So once I run this now, and I print sex, so I just get this. So you can look at it now. So for each particular level of the sex variable, I get the number of individuals there, the events, the median, just like the other table. The only difference is that this time around, we are grouping by a category. So same thing too, also I can get at specific times. So at specific times, you can see it here. This is for the female, for the male. This is for the female. You can look at these particular two tables and compare the risks, or just have a glimpse of the survival between both groups. And also the plots, same argument as the one also I did earlier on. And if you want to read more about the arguments, you just run question mark with your function. If you want to check the arguments, you can just run ggsolve plot and you get details on the argument. So this is for sex. I don't think I put this in the slide. So this is for sex. So you can see that of sex, male. So this is our log rank tests that we did. Is already on the table on the graph. So there's a statistical significant difference between male and female in terms of survival. You can see the survival of female is higher to that of the male. So the male have a lower survival compared to that of the female have a higher survival compared to that of the male. Survival by age group. So this is also similar. We're just removing the missing values here now. We're still using the similar, just what we did earlier on. Solve time dates. You put your survival object in this place. So the same thing to here, survival objects here, then your age group. So unlike the other one, we use sex. Then we can still get our graph. So let's look at the graph. So I think this was what was on the presentation slide earlier on. So you can see a Kaplan-Meier graph. So this is one of the things I'm talking about. The more your levels get, the more it gets clumsy on the graph. So you can see it because we still have these shaded areas. Which signify the confidence interval. It becomes difficult to interpret. So it's all these limitations that make it necessary for us to use the Cox model, which we'll be running later on now. So this is just the log rank test. And this is the log rank test. The log rank test already comes with the Kaplan-Meier, which you can see it earlier on. I'm still going to run it for us to just see how you can get it. So I think, where is it? This is it. It's already inside the function. It's not difficult running survival analysis in R. It's just few lines of code. The just important is just interpreting your results, making sure that what you are interpreting is meaningful. So okay, let me talk about this pairwise. I don't think I talk about it in this slide. So this pairwise comparison. So what this pairwise, if you look at this function, pairwise is just solve different. I'm trying to look at the difference in survival between two levels of a particular category. Let's say age. I have 3, less than or equals to 60 years, 61 to 70, greater than 70 years. I now found out that from my log rank test that there was significant difference between these ages, but I don't know which of them was significantly different. So this pairwise comparison allows us to fish out that particular group that is significantly different. And if you look at this now, you can see between 60 and okay, I'm trying to see if this particular age was even significant. I think was it this place we run it. So you can see the age was significant. So let's look at this place now. If you look at 60 and 61 to 70, the value is 1. If you look at less than or equals to 60 and greater than 70, the value is 0.099. If you look at 61 to 70 and greater than 70, the value is 0.265. So it's possible that difference is likely possible that the difference is between less than or equals to 60 and greater than 70. Since you can see the value is is very low. Even the value is still not is greater than 0.05, which is our p-value. But our log rank test is only telling us that there is a likely significant difference in these particular variables that are looking at. So this is more or less like a post-hoc test that we're conducting to find out which of these variables that are in which of these levels under the age category are significantly different from each other. If you find out that you are not okay with this, I think there are other correction adjustment methods. Let me see. There should be other adjustment methods that one can also try on to get various results. Yeah, so these are it. We have Home, Hotchback, Hormel, Bonferroni, BH, BYFDR. So these are the various adjustment method one can use. They should have various results, so one can check that. Then we have the Cox proportional hazard model. So the Cox proportional hazard model is still very simple. It's just a single line. This time around using the Cox pH function, still from the survival package. You have your survival object, at which I say it must have time and date. Time and date must be inside your survival object. And then we have your gender. Then you have your data. So this, well, including only a single category here. All these that are looking at are univariate Cox proportional model. We're only looking at a single category here. So I can decide to run this now. If we run this now, so you can see the coefficient. This is the coefficient here, and this is the hazard ratio here, the exponential of the coefficient, and the value you have is 0.5880. So which means the hazard of female experiencing that event, which is dying, or the hazard of female dying, is 0.5880 lower compared to that of male. If you did not see the other category here, then that category is now your reference variable. It's not usually included because the reference variable doesn't have any estimate because you are referencing it. But the other category you look at, which is your female, now becomes what you now interpret. So you can see it is actually statistically significant. Same thing too, also we can do that of the age and the ECOG performance score. So if you look at these two now, this is the age. You can see the age. This is the coefficient 0.018720. This is the hazard ratio, which is the exponential of the coefficient, and this is our age value. The age is not significant. So, but assuming the age was significant, we can now say that as age increases, the hazard of dying actually increases, or there is a 1% increase in hazard since 1.01889 minus 1. So you can have 1.8 something. So you can say around 1.889% increase in hazard as the age of that particular patient increases. So this is how you can interpret that of your age. So, okay, I think I did that of the ECOG performance. The ECOG. So this is it also. It's also a continuous variable. You can also see it's statistically significant. And this is the hazard ratio. So an increase in ECOG performance increases the hazard of dying by 1.6095. So this year we're just trying to demonstrate the conversion. Can you look at it? So if you take the exponential of the coefficient of sex, you can see you have the hazard ratio. Likewise to also the confidence interval. If you take the exponentials of the coefficients in the confidence interval, you also have the hazard ratio. Now for a multivariable Cox model is where you now combine your categories together to control for confounding. In the multivariable Cox model, let me filter for the missing values here. I'm just removing the missing values. Then the only difference from the univariate Cox models I've already run earlier on is just the addition using this plus sign to add more factors. So you just use your plus sign to add more factors. So I'm going to run this. I think we actually have age. Let me use the age group. I think I did an age group. So this is the summary. I want us to use the forest plot for interpretation. So this is the forest plot here. This is it. Cox multi is much more easier on the eye. So let me run this to interpret it. So this is the forest plot here. So I think in the presentation slide I had not added this plot. I used the continuous variable. Now you can see we have our age group now. Sometimes this is also one of the importance of categorizing your continuous variables. You're able to see features on possible difference if it exists, although we don't have any significant difference because the continuous variable itself was not even significant. So statistically significant. So that means even the categorical might not also be statistically significant. Where it will be better for you to categorize your continuous variable was when you found out that using the continuous variable was not statistically significant. I wanted to report, and you want to report more or go deeper. You can break down continuous variables into various categories. Then you can now fish out that particular category that you see statistically significantly different. Because out of 5 categories, you can have 4 that are actually similar, and one of them is actually statistically different from the others. So look at the age group now. We have less than or equals to 60. We have 61 to 70. We have 70. You can see their respective hazard ratio, though they are not statistically significant, but you can look at their respective hazard ratio. Assuming they were statistically significant, we can say the hazard of age 61 to 70 dying is lower compared to that of less than those that are less than or equals to 60 years age. For greater than 70 years, we can say the hazard of those greater than 70 dying is 1.40 greater than that of less than or equals to 60 years. Then we have that of the sex, which I've already explained earlier on. We also have the ph.epoch, ph.kano. So, like for this ph.epoch is continuous. Now, to find out which particular ECOG value or number is showing this statistical significance, you can decide to group it into various groups. You can say, since it ranges from 0 to 100, for example, you can say 0 to 10 will fall in this category. We can say it's level 1. You can say then 0 to 10, then 11 to 20. You can group it like that to find out which group is having more effects or is having a higher hazard compared to the other groups. So we have interaction here. So let me run this interaction. So let me run the Cox interaction here. So this interaction. Okay, I'm supposed to be saying, why is it giving me coming? Okay. It's supposed to visualize the interaction. Run this again. Alright, this. Okay. Okay, let me do it like this. I'm coming. So let's just look at the summary. I think that interaction might not show on, it's not showing on the plots, forest plots. I think it should show on the summary. Okay. Alright, this is actually more than what else. So it's not showing on the plots, showing on the, okay. So this is it now. Okay. So now this is how you can interpret interaction. Interaction is whereby I want to see how a particular variable affects another predictor variable you have. Now the reference category in this place now is if you look at this now, I think it's not there. I think the sign is now. Let me use this. Okay, yeah, this is it. This is it now. So this is it. So this is the interaction. So this particular column, so these are you put the interaction. You use your sex, you have to put them individually. Then you put this particular asterisk which indicates interaction between those particular two groups. So how we interpret the interaction is that the reference group for your interaction is usually the reference categories interacting. Okay, the reference group for two variables that are interacting is actually the interaction between the reference of those two variables. For example, now the reference value of our sex is male. The reference value of our age is female, is less than or equals to 60 years. So which means when we're trying to interpret this, let's assume this interaction is statistically significant because you can see that what the interaction is not statistically significant. Though this should not be surprising because the age itself was not even statistically significant. So what this interaction means is that the hazard, we're assuming now that it's statistically significant. This is our hazard ratio, 0.714. So the hazard of a female that is 61 to 70 dying, the hazard of a female 61 to 70 years dying is 0.714 less compared to that of what a male that is 60 less than or equals to 60 years. Same thing too also if you go to this particular group. The hazard of a female that is age 70 above dying is 0.642 less compared to that of a male that is less than or equals to 60 years. So this is how you interpret interaction. One of the reasons why sometimes you use interaction is that sometimes you will notice that a particular maybe from literatures you will notice that a particular value or a particular variable is affecting your outcome from the introduction of another variable. A typical example is heart disease in terms of smoking and coffee. So you can see that you might find out that coffee is affecting heart disease, but by the time you now introduce smoking as a variable, you now find out that it was actually those that smoke and they take coffee that actually have outcome of heart disease, not those that have coffee and don't smoke. Without adding smoking, you are thinking that it was coffee consumption that was causing heart disease. But by adding the smoking, checking for the interaction between smoking and coffee, you now find that it was actually those that were smoking that take coffee that actually have heart disease and not those that were taking coffee and not smoking. So this is one of the importance of adding interactions, mostly when though interaction usually complicates the model, but at times it's best to just add the few that you think are meaningful to find out how various covariates are interacting with each other. So this is it for this particular session today. This is the end of the session. I don't know if anybody have questions among us. Any questions? Okay, is there any questions? Okay, someone is asking what is the concordance value. I'm seeing that in the message. Okay, let me check let me share my screen. Let me show the concordance value. I think I left that out. I think one of our model, let's see. Yeah, this is it. So someone's asking about concordance value. So the concordance value actually shows how well the model discriminates between subjects who experience an event earlier or later. So, for example, now if person A has a higher predicted risk than person B, and person A actually experiences the events before person B, so that particular pair is concordant. So, person A, let's say for example, two gender, male and female. So, the male might have a higher predicted risk of dying compared to person B, but the male might have experienced the events, or okay, male and female now. It's possible that the male might have a higher hazard ratio of experiencing the events compared to the female, but the male might have already experienced the event before the female. So you can see that what these two particular pairs are concordant. So the value usually ranges. We have 0.5, whereby no better than random guessing. So if you look at this particular place now, our value is 0.641. So this means that we have a very poor discrimination. If we have a value of 1, we have a perfect prediction. Or if we have a value of 0.8 to 0.9, we have a very good discrimination. So the higher the value, the better is our Cox model. So is that clear? Okay, I hope this was clear. The person that has Eric's uncle. Okay, yes, thank you. Okay, any more questions? Okay, I think we'll call it a day. Thank you very much, everyone. Thanks, Kiara. Thanks, Akin. Thanks, Eric. Thanks, Ifyoma. Thanks, Lowell. Thanks, Neva Mujire. Thanks, Osiroko. And also thanks, Peter Liu. Thank you very much, everyone, for attending. I don't think we have any more questions. Okay, someone said they type other questions in the chat earlier. Let me check. Okay. I think I'm seeing the questions now. Okay, first question is that is the time variable recorded only once during the study? No, time value is time. That time is time to event. You're actually recording that time for each patient, because if the person was censored in the study, you record the time. If the person died, you record the time. But if the person is still in the study, then you're not recording any time till something happened to that particular person or individual, either the person died or census, maybe lost to follow up. So if the person even exceeded the study, then you just record the time of your study for that particular individual. If the person exceeded the time of your study, you just recorded the time till your study ended. So that is what that particular time variable does. The next question is at time 0, if left censoring occurs, how will that play out in the probability estimation? Well, most of the times the thing is that the left censoring is even rare. So most of the times for survival analysis is you will only just come across that particular right censoring. So the left censoring is very, very rare. Though there's also ways of handling the left censoring. But most of the time you come across just the right censoring, because that is what is even more realistic when you're working with survival data. That's the most common things that you see in your study time. The left censoring is just possible something happened to the patient maybe before starting your study, or things like that. Sure. Okay, so I hope everything was clear. Okay, well, I think we'll round up from here. It was nice having all of you on this particular platform. So thank you very much.
Recording stopped.
Okay. So, who was asking of my contacts?